so good. And I'm so excited about being the session chair that I'm going to miss the talk for my own paper. The first paper we're going to hear about is Macarama, optimal oblivious RAM with integrity. And the authors are Surya and Nikon Vafa, and Surya will give the talk, please.
Testing. Okay. Hi, everyone. Today I'm going to talk about Macarama. This is an oblivious RAM construction with optimal overhead, even in the malicious setting. So this is based on joint work with Nikon, it's right here. So in this work, we consider the problem of remote RAM computation. So basically consider a user who wants to perform a RAM computation, but doesn't have enough local space to do it. So one thing he can do is use a remote RAM server, let's say AWS. So now the user can perform the computation on the server. So when I say RAM computation, I mean that this user is going to send read and write requests to the server. And then the server is just going to respond to the read and writes. But now how can you ensure privacy against such a server if the server is curious? So one immediate idea you might have is to encrypt all of the data. So the user is going to store a key, you're going to encrypt everything that goes to the server and decrypt everything that comes back. But turns out this is actually insufficient because even the access pattern to the database can leak information. So for example, consider a scientist is conducting a medical study. And let's say he encrypted everything on the server, but he makes a lot of accesses to the hard data portion of the server. But now the server can say, well, I don't know who these patients are. I can still tell that many patients have heart issues. So you're still leaking information. So even the access pattern can leak private information. So to combat this, Goldrack and Ostrowski proposed the notion of oblivious RAM. So ORAM is basically a layer between the user and the server. So now the user is going to send the read and write queries to the server instead, and to the client instead. And the client is going to take this query and transform this into a bunch of query hats to send to the server. And throughout this talk, think of this server as being passive and only responding to read and writes, no additional work. And then finally, the ORAM client now generates some response for the user. So for this to make sense, we need correctness, which basically means that from the user's perspective, the responses make sense. They are the corresponding responses to the read and write queries. So the second property we want is obliviousness, which is basically that all the queries here leak no information about the underlying queries. So in symbols, the list of all the query hats can be simulated knowing only the number of queries made to the server. So for example, with our remote RAM example or a file storage platform example, a user can simply just run an ORAM client locally on her computer to interact with the server. So now the server can only see the access pattern and it cannot learn anything because there's an ORAM client in the middle. A second interesting example is with secure hardware enclaves. So you can think of a secure hardware enclave as basically this lockbox inside an untrusted server that is completely tamper-proof. And now what you can do is you can use this small lockbox to bootstrap the security to the whole server. So I'm very much simplifying things here. But so now if you run an ORAM inside the Intel SGX, which is protected, the access pattern to the external server is now private. So you prevent information leakage even in the outside server. So this is basically like bootstrapping a small trusted memory to something bigger. And this is very cool. And it's in fact used in the real world by Signal, which is a messaging app for private contact discovery. Okay, so what do we care about in terms of ORAMs? We have two efficiency metrics that we care about. So firstly, we care about the local space that the ORAM needs to store. So this local space is basically the amount of trusted private storage that the ORAM needs on its side. And for this whole talk, think of this as being 01 words or roughly log n bits. The second thing we care about is overhead, which is basically the number of query hats per underlying query. So we want this communication here to also be small. So what do we know in terms of ORAM constructions? So the original paper of Goldrack already achieved something sublinear, which is very exciting. So it achieved square root n log n. And there's a series of subsequent works that achieve this very polylogarithmic overhead. And finally, recently, Optorama achieves log n overhead. This is very exciting because there's also a matching lower bound of omega log n, even against computationally bounded adversaries. So against a PPT adversary, log n is basically the best you can hope for. So this is Optorama is in fact optimal. Yes, so why are we not done? Because so far the power of the adversary that we have considered, it's only an honest but curious adversary. So basically, like a detective that's looking at this transcript here and trying to infer information from this. But in reality, the adversary can actually do a lot more. So consider an adversary that also tampers with the database and corrupts all the responses. So now you have a devil here who corrupts all the server responses, and the server contents and all the responses are also corrupted. What do we know in this setting? So it should be quite clear immediately that correctness is probably violated, because you can think of a server that just never cooperates. And but surprisingly, even obliviousness can be affected. So at a very high level, the reason for this is that after a corrupted response from the server, this third arrow here has no more privacy guarantees. In the honest but curious setting, we only have a privacy guarantee if this second arrow here is correct. So basically, with all of our applications before, we have no more privacy guarantees. So this is a very important setting to consider. So looking back at prior constructions, so turns out the first 3 constructions are actually known to be, it's possible to make them maliciously secure with just O1 overhead using various techniques. But it's not known if Panorama and Optorama are maliciously secure. And in fact, in our paper, we show some attacks on these constructions. From the lower bound side, it's interesting to ask, maybe log2n is actually the best you can do. So is there any stronger lower bound? And this is exactly what we ask in our paper. So the question is there a maliciously secure ORAM construction with O of log n overhead? And yes, there is. So in our work, we construct Macarama from just one-way functions. And this is a maliciously secure oblivious RAM with O of log n overhead and O of 1 local space. So a few comments about this. So again, this O of log n is optimal. And so, in some sense, you can think of getting malicious security for free, where free, I guess it's subjective, but I think it's free. And I want to point out that our maliciously secure ORAM is still in this passive model where it's only responding to reads and writes. As long as it's honest, there's no extra work you expect from the server. And finally, I'll make this connection clearer a little later in the talk, but this one-way function assumption here is actually also necessary for a maliciously secure ORAM construction. Okay. So putting it back in the context of this picture, basically we have a log n overhead ORAM with malicious security. And as a corollary, we also show that omega log n is a tight lower bound for the malicious setting. Okay. So now I don't have much time to talk about the full details of the construction, but I wanted to give a flavor of it. So our starting point is Optorama, which is an honest but curious ORAM with the optimal O of log n overhead. So I'll talk about 3 main ideas that we use. So the first thing we do is we thought about memory checking, or more specifically, something like a Merkle tree. So maybe you could just overlay a Merkle tree on top of the construction. The second thing we do, which probably you might have guessed from the title of our paper, is we also thought about authenticating all writes with MACs. And finally, we mac and cheese, and I'll explain what that means at the end of the talk. Okay, so memory checking. So an immediate idea would be to basically overlay something like a Merkle tree, or more generally a memory checker, on top of the ORAM construction. So a memory checker is basically a protocol that detects if a server is responding honestly to queries. So in terms of pictures, it's similar to the ORAM as it's a layer between the user and the server. So now the user sends a read or write query, the memory checker talks to the server, and for the correctness condition, either this memory checker is going to abort or send back a correct response. So if it ever decides to send back a response to the user, it better be correct. And again, for this to be non-trivial, you need this completeness condition that basically says that if the server is honest, you're not going to abort. So basically, you're just going to make sure the server is cooperating with you. And if you ever detect any incorrect response, you just abort. And if this is a lot, maybe an easier way to think about this is exactly what we expect from a maliciously secure ORAM without the obliviousness condition. So basically, we do not care if this leaks information about the underlying queries. We just care that the final response is correct. So what do we know for memory checkers? So first, we care about both local space and overhead. So for O of 1 local space, we know that anything with sublinear overhead better imply one-way functions. And this is a result from our problem. And this is exactly why our maliciously secure ORAM construction also needs one-way functions, because it implies memory checking. So the best known constructions for ORAM have an O of log n overhead. And for something concrete to think about a Merkle tree. So the memory checker is going to store the root of the Merkle tree. And every time it makes a read, it's going to access the full path on a binary tree corresponding to the leaf that you're reading. So that's the height of the binary tree is O of log n. So that would give you O of log n overhead. So it turns out there's also a lower bound of log n over log n overhead for a special class of memory checkers that are deterministic and non-adaptive. And it turns out all existing constructions follow this framework. And so you can't really hope to beat this O of log n by too much. So intuitively, this seems to solve our problems, right? Because but curious ORAM plus memory checker gives you a maliciously secure ORAM. And the idea is as follows. You put the memory checker in between the ORAM and the server. And now the maliciously secure ORAM is basically the composition of the memory checker and the ORAM. And the reason this is secure is because the memory checker ensures that every response back to the ORAM is correct. And once you have this correctness, you can invoke the honest but curious security of the underlying ORAM to get a maliciously secure ORAM in this picture. Great. But this isn't efficient enough because I promised you O of log n overhead ORAM. But for honest but curious ORAM, we know we need log n overhead. For memory checker, the best we know is log n. So this only gives you log squared n. So what are we going to do? So I guess a natural question to ask is memory checker the correct thing to look at? Or is there something weaker we are okay with? Like, does a weaker compiler suffice for this type of composition argument? So basically, if I have some pi here that I want to compile with the ORAM, and I want to make this a maliciously secure ORAM, can it be something that's not a memory checker? And in our work, we say no. Actually, if pi is something that compiles the ORAM with overhead L, a blow up L, this must imply a memory checker with blow up L. So basically, pi better itself be a memory checker. So yeah, we're sad. So to summarize, so memory checking says that if I expect to have some O1 blow up post compiler, it also implies the O1 overhead memory checker. But we don't know how to do this. And yeah, so best memory checkers have O of log n overhead. So this seems very unlikely. So how can we proceed? So I think the big picture takeaway here is really that we can hope to achieve this type of result in a black box sense. And we really have to open up Optorama and look at all the details of the underlying construction. Okay, so the main observation we had is as follows. Do we really need the full power of memory checking for Optorama, like specifically this construction? So what if Optorama can tolerate some lies here and there? So for example, I send a query, the ORAM sends a query hat, gets back a possibly corrupted response, but the ORAM's like, what? It's fine. Maybe the server lied, but I'm okay with handling this later. If there's any subroutine like that, we can maybe try to think about using a weaker but more efficient batch notion of memory checking. So that's exactly what we do, and this is called offline memory checking. So an offline memory checker is basically a memory checker with a slightly weaker guarantee. So you should really think of this as batching a bunch of queries. So the user is sending a query, it gets back a possibly corrupted response, it does it again and again and again. And at the end of the day, it says, okay, I'm down. Now tell me if something had gone wrong in some of my earlier queries. So now the memory checker talks to the server again and determines whether anything had gone wrong and sends back either everything was correct or something went wrong and it aborts. So is a much weaker correctness guarantee here. So again, it's just really batching a bunch of queries and checking if something went wrong in the batch of queries. So the exciting thing about this is that it gets us closer to what we want because this is an O1 amortized overhead. So we know how to do offline memory checking with O1 amortized overhead. And the good news is some routines of Optorama can actually be done with offline checks securely. But of course, offline memory checking is very weak. So you can't hope to only offline memory check the whole construction and get away with it. So offline memory checking alone is insufficient, but it gets us very close. So we need another technique. So let's go back to something a little simpler than memory checking. So let's consider MACs. So basically now you're going to have a MAC layer in between the ORAM and the server. And for every single write, you're going to append a tag. And every time you read, you just verify that this tag is correct. and either abort if the tag is incorrect or send it back. Okay, so this basically ensures that this server cannot send back junk. It has to it can only send back information that it's already seen before from the client. But there's an issue with this because the server can still do what is called a replay attack. So what do I mean? The server can basically rewind and send back old data corresponding to some address. And now, because of the correctness of the previous check, you better the verification better still pass. So this is not secure. And in fact, this breaks both correctness and obliviousness. So if you take existing constructions and add this type of MAC layer in between, it's actually insecure. So this is on its own is not secure. But a standard technique to fix this type of replay attack with MACs is to basically append a timestamp. So now the MAC is also going to have a global counter. You're going to add a counter to every tag that you make. And whenever you read, you also retrieve the counter. So now along with the check with the MAC, you're also going to check if counter was the time of the most recent write to a given address. So if you're able to compute this thing, if you know exactly when a certain location on the server is accessed, you're good. But unfortunately, we show in our paper that some of the subroutines in ORAM would require omega of n bits to even verify this type of timestamp. So this is not going to work on its own. Okay, so how can we proceed? Okay, let's combine everything we have. So the main ideas of our paper are that first, you're going to use MACs, right? So whenever the scheme is timestampable, so that means you can compute the counters in low space and efficiently, we can just MAC and get away with it with O1 blow up. Then we're going to check efficiently and securely. So you use the offline memory checker with amortized O1 blow up. And we have to use this in a very careful way because you can't offline check everything. So we have to really go through the algorithm and choose when to do this. And in some cases, we have to interleave timestamping and offline checking so that like parts of the algorithm that are checked in different ways and we have to interleave them. So yeah, we have to mac and cheese, check efficiently and securely. So like, like you have a malicious server and you're like, Superman, come save me. And then like Superman comes in with a mac and cheese. Are you eating mac and cheese right now? Okay. And yeah, this was created by Dolly. I just said make Superman holding mac and cheese, and this is what it gave me. Very exciting. Okay, to summarize, basically we construct Macarama in our work, and this is a maliciously secure ORAM with O-block and overhead and O1 local space. So another very interesting interpretation of this result is that it's actually an oblivious memory checker. So that means it's a memory checker with the additional property of obliviousness, and this matches all the known memory checkers. So from the memory checking side, we get obliviousness for free. And our assumptions were also provably minimal because one-way functions were necessary and sufficient for this construction. We also showed that a black box overhead preserving compiler has a huge bottleneck because you have to have better memory checker constructions. And instead, so we developed memory checking techniques in the ORAM setting. And we really hope that these techniques can be used for any future constructions or any future improvements of, say, ORAM. So I'll leave you guys with a few open questions. So firstly, our ORAM construction has a very large constant factor. But this is just inherent because ORAM uses sorting networks which have large constant factors. So interesting open question is to reduce this constant factor. Another question is whether there exist memory checkers with O1 overhead, or if we can come up with a lower bound for all classes of memory checkers. So yeah, again, the best constructions will only have O-block and overhead. Okay, thank you very much.
Questions? Don't be shy, please.
Oops, sorry.
So
yeah.
So in your slides, you said that your word size has to be bigger than log n. Is this?
Slightly
Do you
bigger.
think this is somehow fundamental that you need this, or is there hope to get low, like actually
Yeah.
log n size words?
So we need omega log n word size. And I think this is somewhat inherent because if you think of, let's say, like a memory checker construction, let's forget about ORAM. A memory checker construction, like all the hash sizes in the Merkle tree have to be omega log n bits, because otherwise you could brute force hash, right? So to be secure, you need every single hash in the tree to be a little bit bigger than log(n) bits so that you're secure against polynomial adversaries. So I think this is somehow inherent. Yeah.
I also have a question.
Yeah.
So Optorama has very big constants.
Yes.
As you said, can you give some estimate of the overhead of your construction, the offline,
Yeah.
online checking?
Yeah. So the thing, I think offline checking, the construction for offline checking gives you like overhead of maybe 2 or 3. So that helps us a lot. So I think our overall, okay, I'll be very, very pessimistic here, at most 10. I think the constant overhead is at most 10. I think we didn't optimize for it, but I think you can like do a lot of pre-processing as well to like make this like very small, maybe like 3 or 4.
Any more? Let's thank the speaker again.
Yeah.
Okay, so our next talk is tri-state circuits, a circuit model that captures RAM. It's by David He, Vlad Kolesnikov, and Rafi Ostrovsky, and David will give the talk.
Okay, thank you very much for that nice introduction. Yes, today I'm going to be talking about something called tri-state circuits. So tri-state circuits are a novel model of computation. So what I want to do today is tell you, first of all, what is this model of computation? Why do we care generally? And then why do we care in cryptography? And more specifically, why do we care in the realm of secure multi-party computation, where this is most relevant? Okay, so in computer science theory, and specifically in cryptography, we're big fans of Boolean circuits. Boolean circuits are great because they're incredibly simple. Right? They're made up of these individual gates. The connections between all of the gates in the circuit are statically decided. Each gate talks only about a constant number of wires. They're just very easy to work with and reason about. This makes them convenient for making protocols that work with Boolean circuits. On the other end of the spectrum, we have a model like the random access machine model. Random access machines are also a great model of computation because they're excellent for talking about algorithms and applications. They kind of model what our everyday computers do. And so it would be nice to have, for example, cryptographic protocols that work with the RAM model rather than the Boolean circuit model. So what would be extremely convenient would be if we had some kind of reduction from RAM machines to Boolean circuits, some kind of efficient compilation. Take your RAM machine, compile it down to Boolean gates. That way we could continue to work just with the Boolean gates and get all the benefits of the random access model. Now, unfortunately, we don't have an efficient reduction of this kind. And in this talk, the word efficient, I'm going to mean quasi-linear. So what you would really like to have is if the runtime of your RAM program is, say, t steps, what you would like to have is a Boolean circuit which has size quasi-linear in t. And that would be very, very convenient, but unfortunately, we don't have reductions of this kind. So what I want to tell you, oh, yes, and the key challenge here, like why don't we have such reductions, is because inherently it's just somewhat difficult to emulate the key feature of random access machines, which is this random access capability, right? You just need to be able to go look up into some large main memory. This is just sort of inherently at odds with the Boolean circuit's static connections. So what I want to tell you about today is a relatively simple modification to Boolean circuits that we call tri-state circuits. And what's really interesting about tri-state circuits is that there is a reduction of this kind. You can emulate RAM with a tri-state circuit of quasi-linear size. Okay. So later in this talk, I'm going to describe this model to you, and I'm going to give you at least a sense of how you can construct RAM. I'm not going to have time to show you the full construction. But before I do that, I want to talk about why we care about this in the context of cryptography. The main application that we've looked at is Yale's garbled circuit. So hopefully, as most of us know, Yale's garbled circuit is one of our fundamental techniques for achieving secure multi-party computation. The idea is that, in the simplest case, we have two parties that want to compute some program on their private inputs. And Yale's garbled circuit is kind of a fundamental technology that lets us do this. And we really like garbled circuits because it has some very nice properties. In particular, it enables constant round multi-party computation protocols, and also it relies almost entirely on symmetric key cryptography. It makes it very simple and fast. On the other hand, when you talk about traditional garbled circuits, it has this inherent problem, I would say, that you have to talk about Boolean circuits. And this makes it difficult for Alice and Bob, the garbler and the evaluator, to talk about the kinds of programs they might want to talk about, because they can't run RAM algorithms on their data. Now, it turns out that there is a technology called Garbled RAM, which takes garbled circuits and scales it up to the RAM model. Okay, so again, the idea here being that the parties just agree on some, say, high-level program and just run it on their private data, and everything runs in quasi-linear cost. So there are many results in the space of garbled RAM. It's a fast-growing literature. I put here just some of the main papers that really target how to improve the algorithmic costs of semi-honest garbled RAM. But one thing I want to argue is that existing garbled RAM constructions are in some sense monolithic. And what I mean by this is that they don't talk about circuits. They have to somehow interleave multiple concerns about things like, how do we garble gates? And at the same time, how do we handle the actual algorithm of looking something up from memory and incorporate things like oblivious RAM, like we heard about in the previous talk? This just makes the technology difficult to work with. It makes it hard to understand, even for experts in the field. And in particular, I want to argue that it makes it difficult to improve. It's kind of hard to get your feet wet and actually start working with this technology. So what we did in this work is we adopted a different approach. Again, I'm arguing that there exists this model of computation called tri-state circuits, and we took a two-step approach. First, compile the random access machine to tri-state circuits. Now, I'm not going to argue that this is somehow simple. This remains relatively complicated. You have to work with things like oblivious RAM. I'm not going to talk about most of the details of how this is done here, but this is still complicated. But you are not thinking about how to do gate garbling. You're not thinking about garbled circuits. You're really just working with models of computation, and this makes it very nice to do this transformation. And the real key benefit is once you've done this, the step where you go from tri-state circuits to garbling of those tri-state circuits, this part is, I would argue, quite straightforward. In fact, I would argue that most people in the room who are familiar with how garbled circuits work, after understanding this tri-state model well, would be able to figure out on pen and paper how you actually do the garbling. Now today, unfortunately, I'm not going to have enough time to really show you how this is done. I'll refer you to our paper. And again, I want to stress, it's basically the thing that you would expect to do once you see how the gates in this model work. Okay, so I'm arguing so far that what we achieved is we sort of decomposed this garbled RAM problem into pieces. Is this all we did? We just buy modularity? And the answer is no. And so what I want to argue is what we were able to do is come up with state-of-the-art improvements to garbled RAM. And informally, I want to say that the reason we were able to do this is because the introduction of the tri-state circuit model made it much easier to think about garbled RAM. And this is why we were able to come up with state-of-the-art improvements. So in particular, we achieved state-of-the-art improvements in the cost of garbled RAM, both in the semi-honest and the malicious model. In some cases, the malicious model by more than a factor security parameter. So these are substantial steps forward in this technology. And it comes down to the fact that we have this simple model of computation that we can think about. Okay, so for the remainder of this talk, what I want to do is actually show you, all right, what are the details of the tri-state circuit model? How does it relate to Boolean circuits? And at the end, give you a sense of how do you actually build random access machines from this simple set of gates, excuse me. So again, this is a circuit model. So tri-state circuits are circuits, first of all, and they're very similar to Boolean circuits in that they manipulate zeros and ones on their wires. However, there is one caveat here. We're going to add one more value to our wires, hence the name tri-state circuit. Right? If this extra value we're going to call Z, which is of course formally just a symbol, but the way that I would like you to think of this Z, which we call nil, is that basically it means this wire does not have a value. Okay, so either a wire can have a value, can be 0 or 1, or it can not have a value at all. Okay. So what are the gates in this model? Well, there's only 3 of them, and again, they're very simple. They're fan-in 2 gates that operate on these values, and I can just tabulate what they do for you. So arguably, the central gate in this model is something that's called a buffer. Actually, this is a gate that's known to people from the world of hardware. And what it does is incredibly simple. So it has 2 input wires, a control wire and a data wire. And it says the following thing. Well, if this control wire happens to be set to 1, then whatever is on the data wire will flow from input to output. Okay. If the control wire is instead set to 0, then nothing will flow through the buffers. Essentially, the buffer is closed, and the output wire will be nil. It will have no value on it. Okay, so that's the first gate in our model. The second gate, also a very important gate, is what we call a join. So a join just takes 2 data wires, and essentially what it's doing is resolving. I have 2 wires which may or may not have data on them, and I would like to sort of pull them and take data from whichever one happens to have data on it. Okay, so in particular, I have these 2 data wires. Let's suppose the top wire happens to have a value on it and the bottom one does not. In that case, the value will flow through. And symmetrically, if the bottom wire has a value on it and the top one does not, that value will flow through. Now, there's a very important detail about how this particular gate works, because I want to say that this gate executes what I want to say eagerly. And what I mean by this is that if this particular wire has a value on it, that value will flow through to the output wire even before we figure out what is on the other wire. Okay, so if this value has a wire on it, same thing, right? This value will flow through. We can compute the output wire without even knowing what this input wire's value is. Okay, and the final gate in our model is just a basic XOR gate, extended in the obvious way. And the obvious way is that, so it computes XOR if its 2 inputs are Boolean. If either input is nil, the gate output's nil. Okay, so that's the entire gate set. That's basically the tri-state circuit model. It's these buffers, joins, and XORs. And there's one crucial additional detail, which is that we allow the circuits in our model to have cycles in them. So typically, when you have Boolean circuits, we insist that the graph underlying that circuit be acyclic. In tri-state circuits, we relax this requirement. You're allowed to have cycles in the graph. This is absolutely crucial for achieving efficient RAM, and I'm going to show you an example of that next. So what's the high-level idea? Like, why is this model interesting? So this is just pure intuition, but the reason this model is interesting is because it allows a kind of data-dependent execution. What I mean is that the gates in this model, because of this thing I said about join gates executing eagerly, the gates in this model kind of execute in an order that can depend on the values in the circuit. So if I take a circuit and I run it with 1 input, the gates might run in one particular order. If I take that same circuit and put in a different input, it might run in a completely different order. And this is crucial for achieving random access, the random access capability. What I want to say is essentially these gates allow some kind of extremely primitive form of control flow where you can decide which way you go through the circuit at runtime. Okay, so to conclude, I'd like to show you how do you actually use these gates to emulate random access machines. And again, this is going to be, I don't have time here to show you the full construction. I just want to give you the sense of how this works. So to do that, I want to show you an example that really points out what this model can do that Boolean circuits cannot do. So to build this example, I need just a simple helper component. So this is called a multiplexer. A multiplexer is a standard component in hardware. But what it says is, OK, I've got 3 wires, S, X, and Y. And S is some kind of selection bit. So if S happens to be 0, then this multiplexer gadget on the left, I claim, is going to output X. If S happens to be 1, it's going to output Y. So it's just performing some kind of selection. Okay, and I claim this circuit diagram on the left, which is built out of these tri-state gates, it does this. So for instance, if I set S to 0, well, then the top buffer will open up and X will flow through. And again, coming back to this eager behavior, the crucial point is that X can flow through this gadget before we even know what Y is. We don't have to have computed Y at the point that we compute this mux. And symmetrically, for if we set S to 1. Okay. Okay. I'll draw a mux like this. Okay. And now we're ready for our full example. Okay. So the full example, this is it. Okay. Promise it's not too scary. So this example has 3 multiplexers, and it's got 2 subcircuits in it, F and G. Now I'm not concerned with what F and G do. They compute some arbitrary thing. What I would like for you to think is that F and G are somehow very expensive. They're large circuits, and I don't want to include more copies of them in my circuit than I need to. Okay, so on the circuit on the left, I have exactly 1 copy of F and 1 copy of G, and I want to keep it that way. I don't want to include extra copies of these. And I'm interested in the following problem. What I would like to do is I would like to run F and then run G. Or possibly, I would like to run G and then run F. Okay, so I want to run these subcircuits in some order, but I don't know what order I would like to run them until the circuit actually starts running. Okay, so in other words, there's this wire S in the circuit, and I would like for this wire to decide, do I run G first or do I run F first? Okay, I claim this circuit on the slide achieves this task. So how does this work? Well, you can kind of see, so if I happen to set S to 0, if we remember how these multiplexers work, well, what's going to happen is these multiplexers on the left are going to try to read their top argument, and this multiplexer on the right is going to try to read its bottom argument. So if you just sort of trace what's happening here, well, X will flow through this top left multiplexer, go into F, and from there it can come back to this bottom left multiplexer and flow into G. We get G of F of X. Okay. Symmetrically, if I set S to 1, the opposite behavior will occur, right? First, X will flow to G, then it will flow to F and to the output. Okay, very simple. But what's interesting is that if you try to build this a device that does the same thing with Boolean circuits, and you try to include only 1 copy of F and 1 copy of G, you're just not going to be able to do it, because you don't know which order you should route the output. Should you route the output of F into G, or should you route the output of G into F? You don't know until runtime. And so if you don't have cycles in your circuit, there's simply no way to arrange a circuit like this without including more copies of subcircuits. Okay. So the generalization of this example that I have shown you is something that looks like this. Instead of having just 2 subcircuits, F and G, I have some entire collection of subcircuits. And what I would like for you to think is, what are these subcircuits? You can think of them as something that stores RAM elements. They store things in a memory. So I place all of these subcircuits which store memory elements. And now, because I have created this permutation network, which is just kind of a generalization of routing together these multiplexers, connecting them in the right order, I can connect together these memory elements in whichever order I would like. So the impact here is essentially each of these elements can effectively store something to a memory by inputting something to a permutation network, and they can read something from memory by taking something out of the permutation network. And this is, by building on this, you can get all the way up to something that implements a random access machine. Now, the crucial point here is that it is possible to build such a permutation network where the permutation network is a circuit of size that is at most quasi-linear in the number of gadgets that I have on the right. Okay, so this is what's quite exciting. This is why we're able to get the results I was talking about at the beginning. Okay, so I had to elide a lot of details that we have on our paper. So I will refer you to our paper for more details. So one of the big ones is we have these buffers which run in a data-dependent order, right? These things, the gates run in some data-dependent order. How does that resolve with ideas from cryptography, like the order of execution should somehow be oblivious? Well, we have an answer to that in our paper that defines how you can have a notion of tri-state circuits which are so-called oblivious. I'll also refer you there to see our full RAM construction and also our handling of semi-honest garbling of tri-state circuits and malicious tri-state circuits. And with that, I'll be happy to take any questions. Thank you.
I have a pretty simple question. I'm just curious about that join gate.
Yes.
Like my kind of hardware intuition, like what would happen if one of the inputs is a 0 and one is a 1? Would you get like a short circuit thing?
Yes, so that's a great question. The answer is yes, you get a short circuit. And so I skipped this from the slides because it was taking me too much time. But the answer is basically, we don't allow you to have such configurations in your circuit. It's your job as the circuit designer to make sure that whenever there's a join gate, you never have a situation where you're joining together a 0 and a 1. Now that might sound scary, but the truth is it's quite easy to arrange that this never happens. Yes, okay. Yeah. Okay, so the question was, it seems like what we've done with these cycles is created something like a latch. And indeed, if I could go back to this picture, it looks very much like a hardware latch. But the functionality that's happening here is, I'm going to argue, completely different than what happens in a hardware latch. In particular, there's no statefulness of these wires. This is a true theoretical circuit model in the sense that each wire acquires exactly one value over its entire execution, and then we throw that circuit away. Whereas a latch would have this statefulness, which is key to how it actually works. That's not what's going on here. Great question. Thank you.
So one question for me. You use this TSC idea for garbling.
Mhm.
What about other MPC models?
What about other MPC models? Yeah, so that's an interesting question. We looked into this. What kind of happens is once you get into models where you have interactivity, you unlock more powerful models than this. In the sense that you can envision having a model that's something like the parties are running a circuit and they have some kind of random access oracle. And this turns out to be more powerful than this. You could compile that model down to this, if that makes sense. But the reason that we didn't apply it for other areas of MPC is because they have more powerful models of computation available to them.
Any more? Okay. Thank you, David. So we were fast and early thanks to the speakers, and it's time for coffee.